Hello everyone, this is PH374. I'm Dr. Chani Pereira and I'm assigned around 10 lectures and basically I'm going to do about electron microscopy. Maybe I might wind up at 7 lectures because another lecturer wanted few more lectures to cover her topic. So I might end up at 7 lectures. But yeah, these lecture today I'm going to do about the properties of electron, and this will cover first 2 lectures assigned out of 10 lectures that is assigned to me. Right. So what is an electron? Let's see. Electron, we know, we consider it as an elementary particle with negative charge. And we also know that people talk about wave-particle duality, which was postulated by de Broglie, and that says all moving matter has wave property, and that is given by this famous equation lambda equals h over p. And here h is that is a famous constant, and p here is the momentum, and momentum we can write down in terms of mass and the velocity. So if we can accelerate these elementary particles with negative charge that we call electrons, they will again act as waves. And an accelerated electron in an electric field U will gain energy E and velocity V. We can combine these, we can build up a relationship. The gain of this energy E is equals to E times U. Here simply means the charge of the electron, and U is the electric field. And you all know, if we go in the classical regime, we can use this classical kinetic energy formula, which is KE, or kinetic energy, equals half mv square. And if we apply that mv square, and instead of kinetic energy, we can replace that with EU, and then you can isolate velocity on one side and get the relationship as 2 simply U over m naught. So that is how you get this equation, and then you know that all moving electrons or matter acts as waves. So we can use that de Broglie wavelength here, and we can come up with an equation for the de Broglie wavelength of these moving electrons, and that will be in terms of its rest mass, its charge, and the accelerated electric field. And if you take into account the relativistic effect, then you will have another additional term coming into play, which I'm not going to go into detail today. Right, so this is very basic properties of electron. And what we are going to, in big picture, what we're going to talk about is we're going to talk about electron microscopy. So all of you know, and I'm pretty sure that most of you have used an optical microscope. There we use an optical beam or a light source, optical light source, illuminating the sample, and we observe it. Here in electron microscopy, the main difference is instead of optical beam or a light source, we are using some source which generates electrons, and these electrons are coming towards our sample as a beam. And what we do, we let them go through a high voltage so that they accelerated. They are now accelerated towards our sample, and these accelerated electrons, which they behave as waves. Since we have so many electrons in one beam, that means we have so many waves in that beam. So waves in the beams, we can mainly categorize them as coherent and incoherent. Coherent means they have the same wavelength and all these waves are in phase, nice and clear, like in laser. But incoherent, they have different wavelengths and they are not in phase. So different wavelengths, different phases, all are jumbled inside this incoherent beam. And we always talk about this linear superposition, constructive and destructive interference, because these are waves, and when two waves interact with each other, what happens? They either interfere constructively or they can interfere destructively. So these two basic properties I think you all are familiar of. So I'll move on to the next slide. And the other most important thing is Rayleigh criterion. Now, why we want to use an optical or an electronic microscope is to weave a sample. Now, optical microscopes, after one size, you cannot use it because due to diffraction limit, you won't be able to see smaller particles, particles mostly smaller than 200 nanometers. You can't, use an optical microscope to weave these samples. So to weave them, we use electron microscopy. Why? Because we have high resolution. We can achieve high resolution in these electron microscopes. But then comes the word resolution. Resolution means you have 2 points and they are very closely spaced and you want to image them. You want to observe them. So in order to observe these 2 points as 2 separate objects, your resolution should be high enough, right? So imagine here you have these are diffraction peaks, right? So these are this is the red color is the sorry, I can't, okay, the green one that provides an airy disk. Now you have a particle, let's say a particle, 2 particles closely situated. This particle, when you illuminate it with a beam of light, what happens? It starts producing this diffraction range. We call it airy disk, right? And again, for the second particle, it will also again produce this airy disk. It's a diffraction peak. Now, to observe these two as two separate objects, what happens? The basic condition, that is the minimum condition you should have, is the lowest point of this. Now you have the green diffraction intensity distribution, and green is a diffraction pattern, and you have the intensity distribution there. So in order to observe the first minimum, that means if you just, it's not drawn here, but you can get the idea. If you just go down and, if you just, okay. Let me get a more clear picture for you right here. So if you just check, you will see that if you just trace this path, the first minima of this green color diffraction pattern will be coinciding with the maxima of the other diffraction pattern. So if this condition is achieved, this is the resolution limit. So at this point, you will barely be able to see, just barely, you'll be able to see, okay, there are two objects, not one, two, but barely resolvable. So this is the Rayleigh criterion. And we will go in the next slide, you will be able to see a more clear picture. Right, if I just increase, if I zoom this, you can see here, it's not that clear, but just to get the idea, this is the diffraction maxima, or the diffraction, this pattern from one object, and this is the other diffraction pattern from the other object. These two are closely situated. So in order to observe them as, like barely observe them as two separate objects, the mean condition is the minima, the first minima of this diffraction peak from first object should be directly coinciding with the maxima of the other diffraction peak from the second particle. So in this case, you can barely resolve these two particles. So the mathematical expression for this is now here figure A shows the graph of intensity of the diffraction pattern for a circular aperture. It can be shown that for a circular aperture of diameter d, the first minimum in the diffraction pattern occurs at theta equals 1.22 lambda over d. I'm not going to go into detail here because in optics, I in detail talk about this part. And Rayleigh criterion is basically this equation. Theta equals 1.22 lambda over d, right? So the 2 points are just resolvable if they are separated by an angle 1.22 lambda over d. So okay. Just wanted to show here. So in the diffraction intensity distribution, you will see that is what does this 1.22 lambda over d means, right? So you have two objects, one bulb and the other bulb. They are the two objects, and they are light coming through a circular aperture. Because they're going through a circular aperture, they diffract, and that diffraction pattern is observed on the screen here. And these two objects are just resolvable if the condition, like first minima of the other one object, is directly coinciding with the maxima of the other object. And this angle, if we numerically tell them that the angle between these two objects, or theta, is 1.22 lambda over d. Right. Now, that is basically, we talk about diffraction through circular aperture. So light pass through a circular aperture, gets diffracted. But when we are using optical microscope, we are using lens system. And the ability of a lens to produce a sharp image of two closely spaced point objects is called resolution. So we talk about the Rayleigh criterion using circular aperture, diffraction by circular aperture, but now we are going to apply towards the optical microscopes. In optical microscopes or in electron microscope, we use some sort of a lens so that we can converge the beam and then we can produce an image. So to produce an image, a sharp image of resolving two closely spaced point objects is called resolution for that lens. And 2 points separated by at distance x. Now we have 2 point objects and they are separated by a distance x, and they are positioned away from the lens. The distance is d. Then we can use the small angle approximation and say x equals d theta, like s equal r theta, S is the arc length, R is the radius, theta is the angle between the angle of the arc. And similarly, we can use that, and we can come up with, we can just rearrange the equation for the theta, and then we can equalize it to the Rayleigh criterion, which 1.22 lambda over d. And then using small angle approximation, we can come up with an equation for the resolving power, where x is equals, that is, x is the distance between the 2-point objects. It's equals to 1.22 lambda simple d over capital D. And d here is how far the objects are situated from the lens. And x is the how far the objects are from each other. Right, so to get an idea about the capital D and lambda, we'll go to the next slide. So when we are dealing with optical microscope and lenses, we always talk about this term numerical aperture. Numerical aperture is a term that we use, that is, it basically gives you an idea about a measure of the ability of the lens to gather light and resolve fine details. So if you just go ahead and look at this, so you have a microscope objective, it's a lens. Light beam comes in, and if they are parallel, then this objective, this lens will be able to focus it towards the sample, or in other words, the light that emitted from the object will be captured by the lens and will uh, uh, form an image. So D here is how far this microscope lens is situated from the object. And D here is the size or the diameter of the lens. And the angle subtended by the lens at its focus is defined to be theta. So here this is the theta value, and that is of course 2 alphas, right? And why we go ahead with alpha here? Because alpha is easier to find. Since we know this is D, we can half it here. It's D over 2, capital D over 2. And we know this distance is D, and then we can come up with the equation, the sine alpha to be D over 2 over D. That is using the small angle approximation, because if we use this D and capital D over 2, it's going to be tan alpha, and in small angle approximation, tan alpha and sine alpha is going to be equals to alpha. So we can just come up with this equation. And the numerical aperture for the lens is given as n sine alpha. N here is the refractive index of the medium between object and the objective lens. So if you have an air, then you know n is going to be 1. If you have any liquid like water, or it can be oil layer, any liquid, then accordingly you have to change the refractive index. And then you can use this equation given here. You can combine these two equations, you know, this is n sine alpha. Alpha is D over 2D, and then you can use the previous equation, and you can come up with this equation, x equal 1.22 lambda D over D. And or you can simply replace, because most of the time when you work with optical microscopes, the numerical apertures are given. So it's easier for you to deal with the numerical aperture. So in the D over D, the simple D over capital D term can be replaced by numerical aperture, and there will be a refractive index coming into play. So depending on the refractive index of the medium between the object and the objective lens, your resolution will be, or the resolution in the sense, the minimum distance that can be resolved. Now, X here is the distance between 2 point objects, and if we put all the parameters, now if you are given an optical microscope, you know the wavelength of the light used, you know the refractive index medium between the object and the objective lens, you know the numerical aperture, you fit all these details, and then when you get the idea, you know, okay, this is the minimum distance between 2 point objects that I can resolve using this microscope. Let's move on to the next slide. So electron microscopy and microanalysis. Now, microscopies we basically use to get an idea about the morphology in small scales that can go down to micrometer and nanometer. Typically, we use optical microscopy, electron microscopy, ion microscopy, scanning probe microscopy. They mainly offer images, right? So if you want to see how you have developed a nanocomposite and you want to see how it looks like, whether it's agglomerated, whether it is smooth surface, or whether it's bumpy, rough surface, you can put it into a microscope and obtain an image. So it gives you a topographical, morphological image. But in order to see the composition or the structures in small scale, you will need other techniques. Most of the time, these are coming as spectra or diffraction patterns. Now, the electron microscopes they have combined with these spectra to analyze to get an idea about the compositional to get the compositional data. So you get an image and you select a particular area, and then you analyze it using EDX, energy dispersive spectroscopy, or wavelength dispersive spectroscopy. So by doing that, you can get not only see the surface, but also you will get, okay, we have iron here, we have titanium here, we don't have any carbon here. Likewise, you can get the idea about what are the elements that are in my sample. And then to further see, okay, I know that we have iron here. In what form, whether it is Fe metallic form, or whether it is in ionic form, or what are the bonds we have, you can use FTIR, and you can use XPS, X-ray, I can't remember, XPS. You can use XRD, X-ray diffraction, to get an idea about the crystal structure, whether it's amorphous, whether it's crystal or polycrystalline. If it is crystalline, what are the crystalline states? Like if you take TiO2, there's amorphous, it can be anatase, it can be rutile phase. So what are the percentages? Which one is higher, anatase or rutile? To get broad idea about, like, to fully characterize the sample you have, you can use various techniques, and electron microscopy plays a major role here, because that is, I think, very few techniques are available to get image nanoscale structures. So electron microscopy plays a major role there. Okay, why we use electrons? Now, typically, like in conventional microscopy, we use an optical beam. And why we utilize electrons, like accelerated electrons in electron microscopy? We know that these elementary particles, and when they're accelerated, they behave as waves. And because they have wave behavior when accelerated, they can produce images, and they can produce diffraction patterns, and we can tune the wavelength by tuning the energy, right? And charge particle, it's a charge particle, and there will be a strong electron, and there will be a strong interaction happening between the sample and the specimen. And we can use these electron specimen or electron sample interactions to further study about the sample that we are after. And then we can do chemical analysis. Yes, all these things are there, but why electrons? If you just calculate wavelength of a photon with energy 1 electron volt, okay, you are given a photon, like a light a packet. You are given a photon and it has 1 electron volt energy. And you are given an electron and it has the same energy. It also has the same 1 electron volt, right? And then if you just calculate the photon wavelength for the same energy, and if you calculate the same the wavelength for the electron with the same energy, you will see that for the same energy, electron will have much smaller wavelength. So it will be like 1,000 times lesser compared to the photon. So you can see the lower the wavelength, the higher resolution that you can obtain. So that's why the basic reason behind using electrons. Let's move on to the next slide. Right, now we will see what are the electron matter interactions that can happen if we send an electron beam towards a specimen. So these incident electrons, they can primarily interact with the specimen. Some, like very small portion of this incident electrons can directly go out through the specimen without any interactions. We call that direct beam. Part of them can be elastically scattered. I mean, part of these incident electrons can elastically scattered inside the specimen. So, I mean, specimen means you have atoms, right, in the specimen, and these electrons can elastically scatter by these atoms, or they can inelastically scatter. Inelastically scatter means you lose, I mean, this incident electron lose some of its energy inside the specimen. So they are inelastically scattered. They can produce Auger electrons. I'll be talking about these Auger electrons later. And then they can produce secondary electrons and X-rays, backscattered electrons. And each of these interactions, they give unique, I mean, information about this specimen. Like Auger electrons, you can use it to analyze the surface of the specimen. Backscattered electrons, they give you a very good idea about the composition. I mean, even in the image, even if you can't identify exactly what you have, whether you have titanium, copper, or any other element, you can't. I mean, just by looking at an SM image, you can't. But if you get an image through backscatter electron detector, then you will see, okay, I have some different elements here and there. Some are darker, some are lighter. And why they are lighter, why they are darker, why these regions appear darker, or why these regions appear lighter in backscatter, I mean, image produced using backscatter electron detector will be discussed later in detail. And the electron interaction with matter inside the specimen will create X-rays. And if you analyze these X-rays, we use them in EDX, or EDX means energy dispersive X-ray spectroscopy. You can get an idea about, I mean, you image it and the generated X-rays are separately analyzed and produce you a spectrum. So you have the image and you have a spectrum, and this X-ray, I mean, this EDX spectrum is basically use these generated X-rays, and that gives you a compositional idea about the image. So that's why these uh, interactions, they will give you um, a very unique information about this specimen. Right. Now, basically, if we talk about these interactions, interactions can be classified as elastic and inelastic. Elastic interactions means the incoming incident electron does not lose its energy inside the sample. That means it does not transfer part of its energy to the sample. Electron leave the sample with its original energy. So this is the incident electron and this is the outgoing electron. I mean, if the incident electron goes like somewhere far, a little bit far from the nucleus, you know this nucleus is positive, right? We have positrons here and electron is negative. So this nucleus will uh, extend some attractive or some attraction towards this electron. So this electron will try to bend a little bit. It will get deviated from its original path. It does not lose its energy. What really happens is it just deviates slightly from its original path. So that is an elastic interaction. There's another incident electron which goes very close to the nucleus. So the attraction is more stronger because the separation between the nucleus and the incident electron is lower compared to the other scenario. So the bending is higher, right? So it will deviate more. And if there's a very narrow chance, but if the incident electron is going very, very close to the nucleus, there is, I mean, this force, this attractive force can, uh, I mean, uh, turn this incoming electron by 180 degrees and it will leave the sample. I mean, it came in because of this attraction force. It take a U-turn and leave the sample out. And we have the backscatter electron detector position such a way that they can capture these backscattered electrons. They capture it, detect it. We'll be talking about these backscattered electrons later. Electron passes through sample without any interaction. There's no any interaction. It just deviates its path, original path. Its path from the original direction slightly. And electron deflect from its path by Coulomb interaction with the positive potential inside the electron cloud, right? Okay. So these are scattered electrons and this is a backscattered electron. Right, an electron penetrating into the electron cloud of an atom is attracted by the positive potential of the nucleus. This is what I was talking about. So this is the attractive force. We call it electrostatic or Coulombic interaction. And its path is deflected towards the core as a result. So this Coulombic force, F, is defined by Q1, Q2 over 4 pi epsilon naught R square. And R here is the distance between the two charges. In our case, it's the nucleus and the incoming electron. E naught is the dielectric constant. The smaller the R, the larger the F line. It's obvious. And consequently, the larger the scattered angle. So more closer you get to, you come towards the nucleus, a higher scattering angle you will have. So backscatter means it's like a complete U-turn, like a 180 degree. Right. Elastic interactions, we talk about the complete backscattering can occur, generating backscattered electrons. It depends on the charge, the force F which an atom attracts an electron is stronger for atoms containing more positive charges. Now let's imagine your sample. Now, as we all know, if we use a nanocomposite, we have several elements in it. Some elements, they have smaller atomic number, some elements, they have larger atomic number. Smaller atomic number means number of electrons are smaller, number of positrons are smaller, and same as the neutrons. So their nucleus is smaller, right? And some electrons, they are higher atomic number, they have higher number of positrons in the nucleus. So that means they have higher, their nucleus is larger because they need to contain all these negative charges inside. So they have a big nucleus. So the chance of getting a backscattered electron is higher if the atomic number is higher because they have higher, they have bigger nucleus. So the chance of electron going close to the nucleus and getting backscattered is higher compared to a lower atomic number material. So that's why it says atoms containing more positive charges, there's a higher the force which the atom attracts that incoming electron is stronger if you have more positive charged nucleus. The Coulomb force increases with the increasing atomic number Z of the respective element. Right. So if we talk about the inelastic interactions, energy is transferred to the sample from the incident electron using following ways. Now, inelastic means this incoming electron loses some of its energy or part of its energy inside the sample. And this lost energy will produce following signals. It can produce inertial ionization. That means electron is, this incident electron completely remove one electron from the shell of an atom into a vacuum. So you have inertial ionization. Breaking radiation, or we call Bremsstrahlung, that is X-rays, generating X-rays. We will talk about these things in detail in next few slides. And then we have secondary electrons, phonons, plasmons, and cathode luminescence. Inertial ionization means incident electron travels through the electron cloud of an atom, transfer part of its energy to an electron localized in any of the atom's electron shell. What happens? Electron goes into the electron cloud of the atom, and either it can bombard or in other way it interacts with electron localized in atomic electron shell of the atom. Now you know that we have electron shells, right? The atom we have surrounding, in an atom we have the nucleus in the center, and then we have electrons orbiting around, and we call these orbitals as electron shells, K, L, M, N likewise. And if one of these incoming electron interacts and provide energy to these any of these electrons that are orbiting around the atom, and if this transferred energy, or the part of that energy given by the incident electron is greater than some threshold energy or the binding energy means this electron is orbiting around the nucleus, means it is held by the nucleus, right? This electron is attracted towards the nucleus and it is held by the nucleus. Now, if you provide enough energy so that you can break this bond between this electron and the nucleus, that is the binding energy, you can extract that electron, you can remove it from the atom. So that means it goes into the vacuum. Electron, that is complete ionization, right? If you completely remove it from the shell towards the vacuum, that means you have completely ionized the atom. Or what happens if you provide like not the binding energy but energy smaller than the binding energy, what happens? Maybe, just maybe, you will promote this electron from lower energy level to a higher energy level. Now what happens if electron is promoted to the lowest unoccupied level? in either valence band or conduction band, this become energetically unstable because we all prefer to be ground state, right? Not excited state. Then what happens? The electron can drop down from higher level towards a lower level, and it will release that excess energy, and that will generate characteristics X-ray, right? Or that can create an Auger electron. We'll see how that happens. If transferred energy is sufficient to eject electrons to vacuum, you call it the ionization, as I told you earlier. If you provide the binding energy, you can ionize it, right? Okay, so how the characteristic X-rays are produced. Now imagine you have, right, you have the incoming electron coming towards, and what happens? It interacts with the whatever in this element, they are filled because they are in the ground state. Electron shells are filled from the lower state to the higher levels. What happens? This incident electron beam or the incident electron will interact with the ground state atom, and it can eject it to the vacuum, right? If you provide them with the binding energy, you can completely remove it from the shell and move it towards the vacuum. Now what happens? Electron vacancy is created. What happens to the incident electron beam? It originally had E naught energy, and it gave part of its energy to this electron to completely remove it from its shell, and that incident electron now lost some energy and will be going out with a reduced energy, right? Because we removed this electron, there's a vacancy here, and this vacancy can be filled by upper shell electron, right? So we have the KLM. K means 1s, then we have M, L we have 2s, 2p, and then M we have 3s, 3p, 3d. Likewise, it goes on. And here the K shell can be filled by 2p, like that is L. And L1 is the 2s. From 2s to 1s is prohibited. So we don't get any electrons coming down from 2s, but we will get electrons from 2p's, right? So if it is coming from here, we will get a K alpha 1 coming out of the, this energy. If this electron is it jumps down and fill the vacancy here, the energy difference between this level and the ground level will be released, and that will be a K alpha 1. It's an X-ray, and you can detect it, and we can find that it's a K alpha 1. If the electron is jumping from this state to here, then the corresponding energy difference between these energy not bands, it's energy levels, that will give out a K alpha 2. Right. Now, if the vacancy is filled not by an electron from L, if the electron is now coming from M shell, M1 again prohibited because M1 is the 3s state. From 3s, you can't jump to 1s because from 3s to 1s is prohibited. This is basic chemistry. If they're coming from 3p or 3d, we will see. If they're coming from this M shells, that is going to be beta. If they are coming from the immediately above one, that is L, they are alpha. Or if they are coming from the next immediate one, that is going to be beta. Now imagine your vacancy is somewhere here in the L shell and it is filled by M shell. Then what happened? That is going to be L alpha 1, L alpha 2 likewise. Now here K means the vacancy is at level K or electron shell K, and alpha means it is uh, filled by the immediately available uh, electron shell, that is L, right? Even in the electron shell there are different energy levels, and the lowest one is alpha 1, lowest possible one. The next one alpha, next one is 2, so we represent K alpha 2. K is where the vacancy is, alpha is saying that this electron is in the next immediate electron shell, and 2 is in the immediate shell, whether it's the lowest or whether it's the highest or whether it's in between. Just by looking at the number, you can say that. Here, this is K beta, means K means the vacancies in K shell. Beta means now this vacancy is filled by, not by the immediate band or immediate shell. This is filled by the next immediate electron shell. The electron shell is in M now, and it is the lowest possible energy level in the M shell. That's why we have 1 here. Here L alpha 1 means, L means your vacancy is now at shell L, and alpha means it is coming from the immediately available uh, electron energy level, immediately high energy level, and 1 or 2 means it depends, right? You can calculate the characteristic X-ray energy. If you know the energy difference, you can calculate the wavelength and see. So these energy level difference are different for different elements, and so that's why we call them characteristic X-rays. This is basically repeating what I said earlier. Yeah. And yeah, you can just read and see. It's very simple. Now here it's more user friendly. Here is K means 1s, L means we have 2s 2p, M means we have 3s and we have 3p, and N means we have 4s 4p, and then we have the 3d one there. So you have a possible ionization in K shell. That means incoming electron has provided enough energy to ionize this element. Its ground 1s electron is now completely removed, so you have a vacancy here. This vacancy can be filled by from L shell or M shell or N shell, likewise it can go on. Transition may occur from L2 to or L3, but not from L1. Why L1? Because it is the 2s. From 2s to 1s is prohibited. Transition from 3s to 1s is also forbidden, but 3p, they are allowed. Right, so you can just go ahead and see what I'm talking here. It's basically what I repeated earlier. Right, now this is an energy dispersive X-ray spectrum, EDXS, or in short we say EDX, or sometimes we just say EDS, of a gold particle in titanium dioxide nanocomposite. So you can see we have detected titanium, we have detected oxygen, sorry, gold or AU, then we have the oxygen peak, we have copper K, and then we have again have oxygen. So just by looking at this energy dispersive X-ray spectrum, we know that we have titanium, we have oxygen, we have gold. Right. So this is a qualitative analysis. You can say by just looking at the intensity, you can say, okay, now we have more titanium compared to gold. Likewise, so you can image it using the, I mean, we talk about it later. You can get an image using electron microscope, and these electron specimen interaction will generate X-rays, and these X-rays are separately analyzed in the EDX and will give you a qualitative analysis about the sample composition. Right, now let's see what are the Auger electrons. First, what will happen, incoming electron will ionize the atom, leaving an inner shell vacancy. Now, this incident electron will knock out this electron to vacuum, and you have a vacancy here, and this incident electron will leave the atom with reduced energy. Okay. Now, the configuration we have here, it's an ionized atom, which is energetically unstable electronic configuration. What happens, the atom will fill the vacancy with an electron dropping from a higher shell, right? Then what happens? The innermost electrons have a higher binding energy. Why? Because they are more closely situated to the nucleus. They are strongly bound, like strongly attracted to the nucleus, so they are more harder to remove. But outer shell electrons are like they are like far away from the nucleus, so they are less. They are still attracted, but less compared to the inner shell electrons. So there can be, the outer shell electrons can easily be ejected from the sample. So to now the incoming electron had very high energy. It can knock out this innermost electron, ionizing the atom. Now this vacancy is filled by a high electron from a higher shell, right? So electron will drop from a higher shell. The excess energy of the dropped electron transferred to a further electron that might get enough energy to be ejected to the vacuum. Now, when this electron is dropped, that that it releases some energy, and that energy will be gained by another electron, outer electron. And these outer electrons, they are loosely bound, so small energy is enough for them to eject into the vacuum. So they will leave, this electron will jump, and the excess energy will be taken by an outer shell electron, and they will be coming out of the sample, and we call these outcoming samples as Auger electrons. So energy of Auger electrons can be determined by the electronic structure of the ionized atom. So energy of the Auger electron corresponds to the difference between the excitation energy and that of the electron shell where it originates. So the excitation energy basically is the electron dropping from higher energy level to a lower energy level where there is the vacancy, and that excess energy is taken by outer shell electron, and that's the excitation energy, right? And it also depends on the shell, which shell this Auger electron, before it ejected as an Auger electron, where it was residing. Normally, energy of this Auger electron range between 10 to 1000 electron volts. So they are comparatively, they have lower energy because they are mostly outer shell electrons. But this energy range, 10 to 1000 electron volts, they are readily absorbed by the material than X-rays. So X-rays can come out easily, but this energy is readily absorbed by the sample. So only Auger electrons generated at the surface are capable of leaving. Now, if you imagine, now you have an atom deeper in the sample, and that creates an Auger electron, and that Auger electron has an energy range between 10,000 electron volt. But this energy can easily get absorbed by the sample material.
So it won't be able to escape the sample. But if these Auger electrons are produced at the topmost, or the atoms that are in the surface of the sample, they can easily escape. And um, if when you will have the system, the SEM will have Auger electron detectors. These Auger electron detectors easily capture these Auger electrons, and since Auger electrons are escaped from surface atoms, they will provide you a very good idea about the surface. So this Auger electron microscopy, I mean, there's a separate microscope technique called Auger electron microscopy, and it's a surface specific method, because only the surface atoms are on the surface of the samples are can generate I mean they all the atoms can generate Auger electrons, but Auger electrons can escape only if they are generated from atoms on the surface of the sample. Right, so this will wind up my SE, the electron matter interaction and properties about the electrons. I will talk about more uh, in detail about the sample and electron interactions when I'm talking about the SEM and TEM techniques. Okay, for now I'm winding up. Thank you.